So about here was light to matter interaction, which gives us an example of Hamiltonian. Here we had a second order perturbation theory, but today we'll get only first order time dependent perturbation theory. Then all components were like targeting in a center where we had some dynamics of quantum system. Quantum dynamics. And at this side, we had density matrix with space, so some tool to deal with time-dependent phenomena. But today, instead of density matrix, we will do just our old good friend time-dependent Schrödinger equation. So by merging Hamiltonian, Schrödinger equation, and perturbation theory, we will arrive to the quantum dynamics, but it will be non-dissipative and it will be even non-returning. It will be just first steps of the dynamics, like perturbative. So in the limit of short time, quantum dynamics in short time limit. So this is the goal. The plan or motivation for this stuff is that in everyday research practice, we not necessarily theoretical or computational, in general everyday research practice, we do need to probe materials, molecules, substances, and see their response to the stimulus, right? And most popular majority of these probes are just exploring response of the object of study onto electromagnetic radiation in different ranges, right? When we come into this domain, we immediately notice that electromagnetic radiation, unlike static electric fields, static magnetic fields, dopings, impurities, it is something different. It brings us away from approximate methods used before. And there is no question that one needs to use approximate methods, because there are about handful number of problems that can be solved by pen and paper with absolutely correct answers. So one needs, excuse me, approximate solutions. If one would look onto if one would look onto systems that been perturbed by external radiation, we will notice that radiation is time dependent, right? So it's electric and magnetic field that perturb system. It changes at each instant of time. And yes, we can use either numeric solution of Schrödinger equation, or we can use variational or time-independent perturbation to find what are the energies and eigenstates at each time point, right? But then if you select this strategy, you would need to practice an approach that likely you started to hate: transitions between different bases. To my knowledge, it is what you were doing as homework exercises in previous 2 months, right? Like spin when one changes direction of magnetic field and tells what becomes eigenstate or distribution over eigenstate. And here, if we would try to utilize our tools from time-independent phenomena to time-dependent domain, it means we will need to do them over and over again at each time step, which like million of times, which is with modern computers, nothing is impossible, but it's not the best, not the optimal solution. Yes. Well, I cannot answer. I cannot say the answer without formulating a question. Would the electromagnetic radiation or another time-dependent perturbation, like motion of molecules that affect electronic states or collisions with other molecules, would this time-dependent perturbations change energies and wave functions? Yes, they will. But again, the paradigm of thinking of energies and wave functions changing any fraction of femtosecond is a little dangerous for sanity of mind. And in the approximation of the intensity of perturbations being negligibly small, there is a new paradigm to start believing that the basis states derived for system in absence of external stimulus are very good and useful. So we can admit the basis states developed in absence of the stimulus and express new solutions under time-dependent stimulus in this new basis. Make sense? Okay. So if we follow this paradigm, it means we can live comfortably in admitting same energy levels, same wave functions, same orbitals as our system of interest would have in the absolute vacuum without any perturbation. So even if under external perturbations they are changed, they are used as a basis. And if basis is good, it is okay to represent any state in this basis. Okay. So what are your memories about perturbation theory? What does it what did you do in previous half semester? Just tell something. What's the main idea of perturbation theory?
Figure out like your new energies and wave functions.
But like, what are the mathematical protocol? How it is derived? Where are they coming from?
You expand your Hamiltonian with some sort of like small perturbation.
Mm-hmm. So Hamiltonian plus perturbation, and then one does set up a small parameter right in front, and this small parameter is needed for several mathematical tricks. So one of them is to say that in the limit lambda equals 0, it automatically converts this Hamiltonian into unperturbed, right? Okay, and based on this statement, one is looking what would happen to the energies and wave functions if we expand them in series in powers of the same parameter. Does it look similar to what you were doing before? Okay, and the main trick, in deriving perturbation theory is I will probably fit it in this little space. So A plus lambda B plus lambda squared C, insufficient, equals A prime plus B prime lambda plus C prime lambda squared is equivalent to A lowercase equals uppercase A, lowercase b equals b, lowercase c. Does this idea look acceptable? So from algebraic point of view, the polynomial of zeros, first, second order are independent functions. And it is same as in quantum mechanics, we do expansion over eigenstates or over a basis. So if these two polynomials are equals, it means that expansion coefficients in front of each power are equal, right? And both time independent and time dependent perturbation theory are based on this trick, just implemented in a little bit different way. So and in time independent perturbation theory, those powers were applied to energies and to wave functions, right? To the power n, the order of approximation, right? In time dependent perturbation theory, the same paradigm will be applied not to energies and orbitals, but to expansion coefficients. So we will treat our quantum states as a superposition of regular unperturbed basis states with expansion coefficients that can be obtained through paradigm of perturbation theory. Okay, so let's try to do it. And for those with whom we interacted in previous classes, I will give a little disclaimer or a little apologies. I really like interactive style, turning camera to the class and taking little interviews. Right now, at the beginning of this marathon, we just need to speed up. As soon as I feel that we are a little more relaxed and there is more time, we'll return hopefully to this standard thing. I'm just not sure if you can fit everything in the class. So it's not because I like looking my own image, but we need to go over materials quickly. So the Hamiltonian can be chopped onto something that is always the same and thing that comes outside and is small. And we can right away put little lambda parameter. Why this lambda is needed? Again, how to live with it. When I saw it for the first time as an undergrad, I immediately started hating it. But it is a continuous transition. Lambda equals 0 unperturbed, lambda equals 1 perturbed. And we can practice if needed. Here in this audience, we are not mathematicians, but if needed, one can apply like continuous transitions, limits, and stuff like that. Now, we admit that the zeroth order Hamiltonian agrees with set of eigenstates. I can put like x, r, or just any variable, so just keep them. I zeroth order. So it defines set of eigenstates, right? So if lambda equals 0, we just have an eigenstates, and we would admit that they obey the orthogonality. And if someone wants it, it's like integration. J dot ij. Now, when we switch on this lambda parameter, maybe continuously, formally speaking, this zeroth order orbitals will be not eigenstates anymore, right? But we can believe or admit that our wave function can be of all parameters. I just put x, but it could be like x1 to x100, depending on number of electrons. And time can be expressed as a summation of expansion coefficients of orbitals, zero order, and time dependence, right? So the expansion coefficients do match. I selected to match initial conditions. So we do want for our mental sanity to keep this basis and these energies. It just seems more comfortable. I'm not telling that it is one and only one approach, but it's just more comfortable in the limit of this perturbation is small enough. And again, if you're already bored and think that is not needed, just a reminder, these things are developed in order to describe interaction of quantum system with external perturbation, which is time dependent, like oscillatory electromagnetic wave or stuff like that. So if we are not allowed, or if it is our free choice to keep the things, right, then the only stuff that we can change is the C sub I, right? So we are going to find C sub I, like before this instant of time, when we dealt with regular quantum mechanics for isolated systems. Expansion coefficients are once and forever. Whatever you create as initial conditions, then they are maintained. And one can get some dynamics by interference of these superimposed states. So there are rich phenomena like dynamics of wave packets, chemical reactions. They just do not change energy, and they do not repopulate quantum states. But now we will tell that they are time dependent, and our goal is to find how they depend on time, which means we break postulate number whatever 3 of quantum mechanics. So from now on, the state system can leave or enter into the eigenstate, and we will write it down as the perturbative series as you did in the previous half semester. So C sub I zeros plus C sub I, and in zeros order, the time independent because there is no perturbation. Then first order, second order, plus so forth. Does anyone want to object, oppose, argue, or disagree? Or it looks more or less acceptable? Okay, so it doesn't contradict to what you had in previous half semester. So, okay, we can.
I guess I'm confused about what you mean by like the different orders of the expansion coefficients. Because we're only working with the expansion coefficients from our unperturbed system, right?
So
like the wave functions, right? So like I'm confused why we need different orders of expansion coefficients.
If in because we want to generate relatively universal theory that would work for complicated systems. If we would try to describe simple systems like two levels or harmonic oscillators, then one doesn't need perturbation theory at all. One can get all solutions right away. They're exactly solvable, even with external harmonic perturbations. But as soon as we depart from simple systems, analytical solution or even numerically correct exact solutions are not possible. And one needs to look for corrections to the unperturbed solution. while looking into Wikipedia about the perturbation theory, found an interesting note that first application, where perturbation theory was derived and tried to is astronomy, where since in classical mechanics one cannot exactly solve more than two bodies, so if there is a third body, one takes solutions at the level of two body and then includes interaction and computes perturbation. So how motion of one planet affects motion of another if they are far enough. Okay, so I wouldn't say like on the marriage ceremonies, speak now or stay muted forever, but it is like an appropriate moment because right now we are setting up the rules of the game, and from now on for next maybe 40 minutes, you just roll down with just mathematical procedures without thinking too much. So right now there were in principle strategic settings, and from now on we will go to just consequences. So the tool that generates this time-dependent solution is time-dependent Schrödinger equation, right? So ddt of a function minus I h bar Hamiltonian wave function. I'm going to wipe it off and rewrite with a little bit more spaces. So if no one was protesting against this initial concepts, either because you really believe in them or you don't care, the next step would be to plug in things into another and try to find solutions. So we are taking this perturbative expression for expansion coefficients and plug it there. Then we take this wave function and plug it here and there, right? And then we take the perturbed Hamiltonian and plug it into there, right? And after doing this mathematical experiment, we will arrive to something like this expansion, and our practical step would be to establish a quality of the same orders of between coefficients in front of same orders of polynomials. Okay, and basically with like few steps, you'll get the answer that London demonstrated to last Friday on the exam for first part of the class, and stuff that we did last night in the lab. So I'm going to do nothing but a little practice of calligraphy, which probably needs a little bit more space. So dt. So summation over I. The perturbative series for coefficient I and there is a convention to put little brackets for the orders of perturbation theory, and then here one puts the unperturbed wave function and its accumulation of phase I h bar e naught I t. Now it's my time to rewrite the same expression, practice calligraphy once more at the end of the expression, right? So summation of I, a bracket for expansion coefficients, orbital of zeroth order I, and accumulation of phase E naught T. And here we put C naught lambda C1 lambda squared C2 with brackets, index I, index I, index I. And here we put unperturbed Hamiltonian plus lambda H1. So basically, well, I cannot say we are done because you cannot sell this expression to experimentalists who just need an answer predicting spectra, right? But in principle, the scientific thinking is ended from now on until next half an hour. So we just need to open brackets and see what happened and then try to analyze it. So what I'm going to do, if the course will be longer, it would be reasonable to invite everyone one by one, but it will take too much time. I will take writing duties. But what I'm going to do is to extract like open brackets, either by writing or in inside the head, and write down all coefficients that, like what this equation becomes if you set lambda equals 0, right? In the unperturbed case, we'll have C expansion coefficients of 0 order, Hamiltonian of 0 order, expansion coefficients of 0 order, and we will reproduce the same solution, right? If here it is C naught, then we will do what would happen if we take all the coefficients in front of the first order lambda. So it will be C of the first order from the left part, and on the right part we would see we would observe a combination. Hamiltonian of the unperturbed 0th order would match with perturbative coefficient of the first order, right? And there will be another term where perturbation Hamiltonian of the first order would match unperturbed coefficient of the 0th order, right? And if you do want second order, I think it is London who volunteered to deliver it. So it's not my business anymore. But one could take like second coefficient here, then H naught with second order coefficient, and then the first order perturbation and first order coefficient here, and see what happens. Okay. David, please do not move. I hope to use image on the screen as a little cheat sheet. And then after I write the first thing, a couple of things, then we'll move. So or lambda to the power 0, 0th order. So it will be ddt 0th order E minus I E naught T H bar. And in the bracket, we have only unperturbed Hamiltonian. Summation stays here, summation stays there. Ci 0, I 0, E minus I H bar EI naught T. Now, if we look lambda to the power 1, first order, so we would take ddt in this first bracket, we would have, and now I do not write lambda, right? We just make coefficients by the equal powers are equal. So I would take C of the first order, keep the summation yet, wave function of the zeroth order, and time evolution, the accumulation of phase, E not T I. Right? No errors yet. Now on the other side, minus I over H bar. And now in brackets, I would have only the first order Hamiltonian, which is likely time dependent. Otherwise, we do not need the theory. And then after I do have summation over I, first order, right?
0th order in that one.
Yes, thank you. Thank you, London. Zeroth order I by I have a better idea. What if we put no, let's keep it this way. We can simplify later. Zeros E minus I H bar E I not T. And then another term for I over H bar, unperturbed Hamiltonian times summation of I C1 I not I E minus I H bar E not I T. So 1 plus 1. Thank you for catching. So any other errors? Yes.
I'm sorry, shouldn't be the summation of C, the 0th order plus C to the first order? Because in the equation over there, you just replace the lambda with 1.
No. Here is the logic that I'm trying to reproduce. So we are not simply putting lambda equals 1. We explore it as a polynomial of all possible powers, and we make if we go for the first order, we make equal everything in front or everything that is accompanied by lambda in first power on the left is equal everything is accompanied by lambda in the first power on the right. And the C naught on the left is not accompanied by lambda in the first power and lambda, so it's accompanied by lambda in the 0th power that we drop. This approach did confuse me for many years. And the way to live with it would be assuming that we multiply everything by function orthogonal to this polynomial, integrate and delete everything except the right part. We probably are not going to do it, but it's technically possible. Any other errors? Or it looks reasonable. So we open bracket and brackets. That here will be like 6 terms, but we pick up from them only those that have lambda in the first power, right? Okay, David, would you please? Thanks so much. So, and I think no one will punish or criticize us if we move Hamiltonian closer to the inside the summation sign, right? Because the expansion coefficients are numbers, not operators, and we can push them through. So lambda second order we skip for now. So dt summation C first order I naught I E minus I H bar not T. Minus I H bar. So I can put probably summation up front and then keep a bracket in the order of H perturbing Hamiltonian times unperturbed expansion coefficient plus unperturbed Hamiltonian times first order perturbation for expansion coefficient, which is expected to be time dependent. And then we have this I not I E minus I E R not I. See, there is not much thinking. It will be just practicing calligraphy. We already expressed our ideas, and we just need to follow them. So what would be the next step? Probably I would jump back to the other screen. So the expression here in the brackets does have two functions that depend on time. The unknown first order correction to expansion coefficients and exponential, right? And we do have a time derivative in front of it. So we need to help time derivative operator to decide which function to approach first. So it's like derivative of a product. So one thing, and it will be our next step. We will practice derivative of a product. If it is derivative of expansion coefficient, it is something that we need for final answer. In the other term, we will take derivative of exponential that will put the energy to the front, right? So it will be like step n+1, next step. After we do it, there is another step that we can do. So the goal, as we have agreed, as we have decided to pursue, is to find expansion coefficients, right? Or corrections to expansion coefficients. And expansion coefficients are numbers. They are not wave functions. They're not operators. They're just numbers. As many numbers, as many basis states, right? So in the final expression, we do not need to have operators. So those are operators that are modifying wave functions, or if it is, if we go from differential representation to matrix representations, all operators are matrices. So we do not need operators. We need to get rid of this. It's not one. It is my poor calligraphy for a little head to symbolize operators. So we do need to make a trick to convert this equation in a such form where it will have no operators. It should, since it is time-dependent stuff, it should be likely ordinarily differential equation for coefficient C sub I with of the first order, right? And these equations, differential equations, should have no operators. So our step number one is just practice derivative of a product, and next step is to get rid of operators to convert this equation into operator-less form. And there is a standard approach for getting rid of operators. Anyone wants to give a little hint?
Have them act on their eigenfunctions.
Huh?
Have them act on their eigenfunctions.
Yes, right? Did everyone understood London? Then ask him, not me. There are a few people in the class who wants to ask you, what do you mean?
So like with a with our unperturbed system, right? The Hamiltonian times our time independent wave functions just gives you the energy of that time independent function. So like the H0 psi 0, we can just do immediately, right? Because we know that that just spits out the energy. The first order Hamiltonian, I'm not sure how we're going to deal with that quite yet, but I'm sure there's some kind of trick.
Okay, so you are suggesting just to apply this Hamiltonian towards wave function.
Yes.
But okay, this is correct, and we will do it. But in addition, let me expand our horizons. We need an equation for Ci1 of t, differential equation for this object that has no operators and no wave functions. We want to be completely in a space of just numbers, functions of time. And so we need to get rid of operators, and we need to get rid of wave functions, of the basis functions. So here is expanded version of question. How do we get rid of the wave functions?
Multiply by their complex conjugates.
And integrating, right? So if you do have the function that we do not like, we multiplied it by complex conjugate with arbitrary number and integrate over whatever the variables are. Like if it is x, integrate over x. And then it will be the delta function, which is neither operator nor wave function, right? And then Adam knows what to do with delta functions when they meet summation. So you see the strategy, right? So we'll do a couple of tricks, and then we'll go from equations that includes operators and wave functions to the equation that focuses only on functions. Okay. Yeah, let's keep it. Thank you. I'll use it as a cheat sheet. Do you have your permission to erase this starting point? So first step is to practice. Okay, thank you, David. Thanks so much. So I can use this spot, right? It's very generous. Okay, so first let's practice the derivative of a product. So summation and derivative can be swapped because they apply to different types of variables and indices. And then we do have derivative over time of Ci of the first order times exponential and I can put the orbitals outside of this bracket. And this next term where we have perturbed expansion, first order correction to expansion coefficient unchanged. And then we have minus I over h bar zeroth order energy times exponential of the same stuff. Okay, and this equals to it's so short and simple when it is written, and it immediately looks long when you're trying to write it yourself. So I will just reproduce the same stuff as it is written there before next step. So first order on zeros order plus zeros order on the first order. And then we'll put brackets and indices. And here we do have the e to the power minus IH bar and the orbital. So we've done our n+1 step just by practicing derivative of a product. Now we do need to get rid of, thank you, Dave. We do need to get rid of the operators, and we do need to get rid of the orbitals. So the standard thing to do it, thanks to London, is to practice orthogonality relation, because we believe that our helpers who prepared solution of the unperturbed system did provide us with good wave functions that are orthogonal to each other, right? We can count on our partners. So we can do either this integration, complex conjugate, or we can just maybe do a little short annotation, put different index. Do we use letter J anywhere? Not yet, okay. And we can just call it Brian-Cat to avoid the this integration and discussion of how many variables and how to perform the integration. So by liberty of mathematical liberty, we can multiply any expression by the same factor from left and right. Okay. Now, we have the technical aspect, technical question that we need to resolve. Can we allow these wave functions to meet each other and be happy, or they have any barriers in front of them? So if the bracket doesn't have operators in respect to system variables like positions, momenta, like coordinates, one can move this bra to meet this cat and immediately convert them into a delta function. But here, if we do have operators between them, we are not allowed to immediately move bra to the cat side. This is forbidden because we will lose the way how the Hamiltonian, how the operator, not necessarily Hamiltonian, may modify wave function, either bra or cat. So as soon as we do see an operator between bra and cat, we should keep it as is, and then check if you can evaluate. And yes, as London prompted before going to this orthogonality, yes, when we will act by the zeroth order Hamiltonian on zeroth order wave function, we will get just energy. But when we will act by first order Hamiltonian on the wave function, we do not know what it is. We just should keep it as a matrix element. Okay, so I'm going slowly but surely opening this expression, and my goal is to establish happiness of Brian-Cat vectors so that they can happily convert into delta functions whenever possible. So summation over I. If I am lazy, I can replace time derivative by a little dot on the front. Is it okay? It's like a convention of lazy people. So C first order. Whenever needed, we can roll back to DDT. First order, exponential. And you see there is a concentration of thought per square inch is quite low in this derivation. It's like a couple of original thoughts, and then you just practice calligraphy again and again. So I'm doing just bar C1 without dot, unperturbed. E not I E minus I H bar E not I T, and then here we have phi not J for our bra and phi not I for our cat. So for the left part of the equation, they are ready to be converted into a delta function. So let's keep this expression further and see what should we do or what we shouldn't do for the right part. So I can move the bra through the summation sign. This is allowed. Then I am not allowed to move it through the H symbol because it is an operator. So I keep phi J zeroth order, H first order, and then I can allow the cat to move towards bra and pass through this expansion coefficient, like write it down here, phi not I, and then have this C not sub I. So by now if we develop universal theory, we do not know what it will be. It will need to be explained and recomputed at each practical applications over and over again. Okay, let's continue. For the second term, we will have E by J zeroth order. And now by acting on the zeroth order Hamiltonian onto zeroth order wave function, we can practice Schrödinger equation, time independent Schrödinger equation, and replace it by eigenstate of the state I, right? Eigenenergy of the state I, and the state I is not changed. Right? And the next stage of calligraphy, we can put energy outside of the bracket and replace it by delta IJ. So sometimes we can get this delta IJ, and then let's just complete it. So I do not want to stop in the middle. So C1 sub I, close bracket, E minus I over H bar, E not IT, and we do not have this cat function. So again, where we are and what is our goal. We are in the middle of the road. We do need to find the equation for first order coefficient. And as of now, we bypassed all our major problems. So specifically, we did practice orthogonality, and we do not have operators and we do not have wave functions, right? So it is a question that one can solve. But before going to actual solution, we need to simplify it a little bit, right? Just to practice regular algebra. So let's look, I just want to come to a logical step, probably everything universal, and then leave the application, it is not written here, leave the application to after the break. So I'll take a liberty and remove it here, put energy E not I into here. And now let's compare terms in the left and right. Specifically, I want all of us to focus on the second term and first and second term in the right. So they do have the same time dependence, right? It's index I, same time, same Planck constant. They do have the same expansion coefficient of the first order, right? They do have the same unperturbed energy of the zeroth order. And they do have the same delta functions because of convolution Bryan-Cat. So if something, I don't remember how to say it, looks like a cake, smells like a cake, and tastes like a cake, it is a cake, or whatever. Sometimes it's applied to different objects. So if we have identical, and it is the same summation, right? So I think no one will punish us if you cancel this term on the left and right part of the equation. Yes?
I believe on that last line, you're missing a negative I over each bar. Because you have.
Yes. Yes. And I must have it, so it's my fault. Thank you. T+1. So it should be right here. And it should be right here. Yes? Thank you much. It's good eye. So we can, and since we are practicing a bracket here and there, we can just cancel, right, that we are canceling this term, and then it will be just first term times the factor. And here, the arrangement of bracket is a little bit different, but we can do it similar way. So we are canceling this stuff, right? And then we will have only the first term here and first term there. And we are approaching close to universal relation that is applicable to any application. So let's keep it as a bit of a cheat sheet, and I hope I have your permission to erase all this stuff. So summation over I, derivative of the first order correction with index I E minus average bar EI T. Here the bracket should be outside. And then we do have a delta function in respect to indices I and J. And this equals to minus I over H bar summation over I matrix element in terms of the unperturbed. First one is J, second one is I, and we have the Hamiltonian of the first order perturbing Hamiltonian. Not index I. Minus I H bar. Not I T. I would like to invite Adam to the board and perform the thing that I am confident he can perform. Please help. Just guess what will be the next, and I know that you can teach this part.
Next.
Like on the left side.
Oh.
And you can make a like explain it in a visual to those who are maybe some of class attendees see it for the first time.
This is a legendary. Sorry. So we have the Niagara snake, right? And it sees this happy rabbit.
Thank you, Adam. So now I think everyone will believe it. Thank you. In addition, there is a price for this little experiment when the summation sign meets delta function sign. They both disappear, but as a price, everywhere where we had index I, it is converted into J, right? So delta function picks those part of this progression where they are equal. And they're equal only if I equals J. Therefore, we replace it. So we put here C sub J 1 time derivative. We change the unperturbed energy to the J. And then we have minus I over H bar summation. And here we keep the good old letter I, right? So here we picked up one term in the progression, and here we have all terms in the progression. Phi J H1 I C not I E minus I H bar E not I T. So just a little, it would be more comfortable to keep only unknown function and its derivative on the left. So we can practice mathematical liberty once again and divide left and right by this exponential, right? So dividing by exponential means subtracting whatever we had here, right? So I'm inviting you to be with me. Yes.
I think you're another exponential on the left side, because there was two exponentials on that side.
On the left.
Yeah.
The bracket here is placed in the wrong way, and it was the same exponential. So by dividing by this part, we are getting this subtraction of energies. Okay. And then we can just rewrite the expression, maybe again ddt c first order of j, which is function of t, is equals I over h bar summation over I. The matrix element of the perturbation Hamiltonian, one can also call it, just to save time, as first order ji, right? Ci zeroth in ei to the minus h bar, energy difference between level I and level j. So in some sense, it is already an answer. We can integrate it and make it a little simpler, but what do we see here? How do we interpret it? We obtain contributions to our first order perturbation by summation over all other expansion coefficients. They provide the state I provides contributions to state J. The bigger the matrix element, the bigger is contribution from I to J, right? So this one is kind of gate that allows amplitude of probability to leak from state I to state J, right? So it is a meaning of the matrix element. It's a leaking probability, right? So if you put like little, I don't know, pools, connect them by pipes, so it's how quickly it pipes from another to another one. And at the same time, since the expansion coefficient is a quantum object, it will accumulate phase, complex phase. It will accumulate phase depending on the energy difference between initial and final state. If they are in resonance, if they are equal, it will accumulate no phase. If they are far away, then it will accumulate phase quick enough. If you want a simple life, we can set up that we can set up some comfortable initial conditions. So this one is universal and general. You can select initial conditions that C sub I of 0 equals like 0, 0, 0, 1, 0, 0, 0. So only selected state number K is non-zero and all others are zeros. It will be just a little more comfortable to integrate and think about it. But generally, one can do it for all states populated. So if we accept this initial condition, which I think Adam would like because it means it will be equal IK, right? Then we can practice snake and rabbit once again and remove summation, remove the initial condition and get just minus a little higher, minus I h bar summation. Oh, no, I equals K. So we will get only JK first order e to the power minus I h bar E A minus E J 0, 0. Here. So it is for a specific initial condition. And here we have DDT first order of J. So yeah, we are losing chance to get a little break. Let's make a break so that we have it in principle, but we are just few lines. I'm failing my own schedule. Let's meet in whatever 4 or 5 minutes. Special thanks for focusing cameras. It's very much appreciated. Yes.
In that last line on the right side, missing the C not.
No, it doesn't. Because we agreed that it will be delta function.
Yeah.
I just skipped a line, hoping that you believe to Adam that when summation meets delta function, it's like a snake, a rabbit, and they disappear. So everyone is back. So we just formally integrated from 0 to t with the integration variable t prime, right? In the universal situation, we cannot perform actual integration because we do need to know a little bit more information about the specifics of this matrix element, right? But even without the specifics, I believe I can provide a little interpretation that will bring you in peace with this equation. So it's much shorter than anything we did before, but still we need to digest it. So let's do like level number K, level number J. So it is schematic diagram. It's not the actual scientific graph. And this is something like time, and this is something like energy. So I'm not taking responsibility for being precise. It's only like interpretive visual. So we start, and here is like time equals 0. Here is time equals t. So we start at level number k because of our agreement about initial condition, and our system lives in this state. It stays there until time t prime. And as far as it arrives to the time t prime, it jumps to the level j, and it will be found there at the end of the trajectory, right? So it's a little abstract, like trajectories are typically defined for something continuous. Here is trajectory for 2 levels out of all other levels. So it, and after it arrives to the state, no, before it arrives to the state j, it accumulates phase, which is proportional to this time interval to the instant of jump, and it is equal to this minus I h bar e k minus e j t prime. So licks and accumulates phase. Now the integration means that in addition to this trajectory that I hope you do not object about, we have similar trajectory where time t prime is different, a little shorter or is a little longer. And then we will have several trajectories that arrive to the same point, but they will accumulate different phases, and therefore we'll practice constructive and destructive interference that will give some result, right? So this idea of several paths being superimposed and coming from the same final state is a very native idea of perturbation theory. It is developed further in the theory of quantum electrodynamics by Feynman path integrals, which I believe at least one of us, Hadassah, must learn because of her advisor. And if one would have higher than first order, right, it will mean that one can jump up and down, and in the second order you have, for 2 levels, you have only chance to return back. In the third order, you jump up, down, again up. Or if there are more levels, you can jump to another level and then return to the same one. But it is a visual interpretation. The equations look much more uglier and complicated, but it will be the higher the perturbative order, like for second order, there will be 2 integrals and 2 different time integration variables, and then 3, 4, infinite number. Okay, so we are done for the first 50% of today's meeting. Now we should return back to the, so we used time-dependent Schrödinger equation and first order perturbation theory. Yeah, it's too small font, even if I show it to the camera, no you see, but it is what I was trying to draw here, is the application of this universal theory to a practical situation related to our meeting 2 days ago. So we all became experienced and educated about vector potential. If someone asks us, we can reproduce the expressions, but for simple life, we can tell that light to matter interaction is just minus electric field amplitude times dipole between initial and final state, or let's use the J and K. We can, if you want to be advanced, we can do polarization vector times cosine omega t. So H1 JK. So we may want to apply the universal derivation, that universal formulation of first order perturbation theory to a practical problem, to a practical situation where the incident light, like UV radiation, affects HOMO and LUMO of a dye molecule, or microwave radiation flips a spin, nuclear spin in the NMR. The mass is the same, right? So electromagnetic radiation is just a product of this electric fields times dipole, right? And 2 days ago we did care the dipole is matrix is obtained G as by not K charge distance phi J, right? Charge times distance between them. But for today's exercise, we just know that it is some constant times oscillating factor. So most stable, most popular, most correct solution for electromagnetic wave in a free space is just plane wave. When we look onto light to matter interaction, we spent a day on justifying that in a long wavelength approximation, the typical molecule doesn't care about wavelengths. It looks like for electric field oscillating locally, right? So we have only this cosine omega t. And now we can plug in this stuff into here. And upon having explicit values for perturbation Hamiltonian, assuming that electric field is small, we can get the influence of the electromagnetic perturbation onto population of quantum levels in a molecule. Okay. So what are we looking forward to observe? So we do want to practice explicit functions to avoid, right now, we had enough of universality and generality. We want to be simple guys and practice some explicit functions. Cosine can be expanded according to our old bodies that starts with letter E. Right. So thank you for prompting. So e to the power I omega t plus e minus I omega t divided by 2. And multiply by all this electric field times dipole. And if you want polarization field, whatever. So if you plug this stuff into here, we will see that it is 2 terms, and in each term it is a product of 2 exponentials, right? Summation product of exponentials means that we add and subtract their powers, and the result will be an exponential. And integral of exponential is something that I hope you have sufficient background to take, right? There will be an interesting practical step, and I think now I'm much more comfortable. Half an hour or even 20 minutes is sufficient to finish it. So what are we expecting to get? We will have combination of frequencies in the power of exponential, right? Summation and subtraction. Upon performing integration, if you integrate exponential, we get exponential back. But since we need to modify, like here, our integration variable is t prime, and here the power of exponential is t prime times constant. So we need to change variables as a price of integration, and we need to divide everything by this factor, by energy difference, right? And as a result, we will have exponential again, time-dependent exponential, which will depend on final time. Well, like 2 terms, initial and final for definite integral. divided by energy subtraction. So this energy subtraction is expected to give us selectivity. So we will have a subtraction of energies and frequencies in the denominator. And it is expected that at some value of their matching or mismatching, denominator will become 0 and all expressions become infinity. So it will select specific values of frequency. So even before starting this exercise, we may anticipate that the result will be very selective to frequency and system will respond much stronger to a certain frequency of initial excitation, right? So it is one expectation. And another expectation that we briefly covered yesterday in the labs that upon performing the integral of this expression, we will have something that one can expand exponential into Taylor series, and then there will be a very comfortable conservation of factors, and we are going to get an answer that in resonance condition, if it is in absolute resonance, that will be independent of frequencies at all. It will depend only on the amplitude of electric field and value of transition dipole. So if we all are allowed to enter experimental laboratory, or if you have experimental collaborators, so they allow us to their sanctuary, there is an expectation that if one tune laser and transition of a molecule ideally, exactly, then the rate how quickly molecule will be excited or de-excited will be universal, will depend only on strength of electric field and transition dipole rather than frequency. Okay, so it's kind of conclusions presented ahead of time, but now we need to make an effort to arrive to them. Okay. So C first order J T integral 0 to T, and now instead of HJK first order, I plug in minus electric field times dipole JK times E plus I omega T plus E minus I omega T divided by 2, and the subtraction of the energy levels T minus J. We need to have T prime to be rigorous T prime D T prime. So let's slowly, we have plenty of time. Let's like slow down just to avoid possible mistakes. Is it Griffith?
Yeah.
Okay. They do not have J and K. They have lowercase a and b, applying it only to two-level system. So minus I H bar plus E times D. Let's, okay, JK to be universal. Integral 1/2 into here, and then we have exponential I omega minus, let's call it so if you assume that we started from ground state and arriving to the excited, if J is excited, then you can call it minus omega JK. Like it is a, we start from K, we end at J, and here is the frequency omega JK times H bar. Minus minus plus G prime plus E I omega JK minus omega of light T prime D T prime. Catch me if you can. At the last stage, it's very easy to make several layers of errors. And we integrate from 0 to T. So for the first, integral, we will have denominator I omega plus omega k j e to the I omega plus omega kj.
Yeah, the written as JK.
Yes, yeah, thank you. And then we need to plug in values at the upper and lower limit, right? Yes. So we put upper limit t and lower limit will be 0. So exponential to the power 0 is, thank you. Thank you. -1. Then plus the same story. So exponential I omega j k minus omega capital I omega capital omega j k minus omega capital. Here we put upper limit t minus value at the lower limit. Okay. So in some sense, it is the answer. And we did explore it during the lab last night. We analyze what it is and how it looks like. So let's try to analyze it right now. If our initial condition that system is at time 0 is at level k, and omega jk is bigger than 0, and frequency of light is bigger than 0, then first term is oscillating very fast. So it accumulates phase very, very rapidly. And the denominator is a big number. So if the frequency is in the optical domain, it's like 10 to the 15 hertz, some big number. So, which means it will be not correct and universal generally, but for analysis, we can just cancel this term because it will provide smaller contribution to overall analysis. So how would we interpret the second term? So definitely it will be frequency selective, right? So in the situation when omega jk is approximately equals to omega capital, the denominator will become 0 and so it will tend to infinity. So if you assume an experiment of tuning the frequency, the answer, no matter what time, it will tend to be much larger in the resonant condition. So resonance condition. If we do want to explore it in fine details, we can move from expansion coefficient, which has a dimension of probability amplitude, to expansion coefficient square and explore the probability to arrive to the state J, right? And then through some manipulations, one would get, since here is the subtraction, one can put half frequency exponential outside of the bracket, reconstruct the Euler function for sine function here, and then get sine squared of omega jk minus omega divided by 2 divided by omega jk minus omega squared. I'm not sure if we have energy and we want to analyze it this time. Probably we can postpone it. Let me think on the background as we go. But what we definitely need to do in the remaining few minutes is to answer how do we analyze this expression, this answer. And this is something valuable. Until advent of powerful computers, it is the answer that theorists were selling to experimentalists to predict outcomes of experiment. So you just derive equation and use it if you need. But if denominator is 0, if this stuff comes to infinity, is it good to tell a friend, like, go to your apparatus and find that the answer will be infinity? It's like something a little unusual. I'm against infinities unless it is amount of money on the account. So let's see if we can do a little trick. I don't remember if we did it yesterday. Okay, maybe we already either did or haven't, but let me repeat it if we did, or do it for the first time if you didn't. You don't remember? How to simplify? So simplify in the limit of so C1 of T J in the limit of omega equals omega jk. Like on one hand, we see that it's indefinite, it's in infinity, right? But the David, you don't need to change anything. Let's keep it this way.
Oh, I think I see what you're doing.
So e to the power x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, right? It is, in some courses, it is the first equation that one learns in calculus 1. In other, it is swapped, but so Taylor expansion of exponential. What if we call this stuff x? And once again, so it's calculus revisited. This equation is applicable only in the limit x equals to x approaches 0. So if our detuning is away from 0, this expansion becomes less and less valid. But if we approach to 0, and we have this confusion of denominator becoming infinite, we are saved by Taylor expansion, because as closer we approach to resonance condition, we get better and better chance to represent exponential just by Taylor expansion. And since our power, our independent variable, is really small, really approaching 0, it means second power is substantially less than first power. And we probably can keep only first 2 terms. Okay. So I H bar electric field dipole matrix element over 2, and we dropped this term and we keep another one. So exponential is equals 1 plus I omega jk minus omega capital times t plus so forth minus 1 divided by I omega jk minus omega capital. So now we can do a glorious cancellation of 1 here and there. Okay. And then we are seeing that in the numerator, we have frequency difference and imaginary unit. In the denominator, we have frequency difference. And the only thing that is different here and there is time. So we are getting electric field, dipole, times time. So some coefficient. In case we do need probability of, I probably can fit everything left in this little box. If you do need probability to observe the molecule in the quantum state J. So it will be C first order J times C first order J, right? Absolute value squared. So it will be, I had a factor 2 because of Euler function. So E squared D squared H bar squared times T squared, right? And it is what we observed by running a little MATLAB code yesterday. So if we have population of the excited state as function of time through perturbative correction, it looks like a quadratic function, right? So and it is valid in the limit of resonance condition. We used to have few more figures. We had this quadratic that quickly goes past 1, so it doesn't conserve normalization of wave function, which seems like a big sin if we are rigorous practitioners of quantum mechanics. But as soon as we are staying in the small time, it doesn't matter. We just look how quickly it absorbs and doesn't absorb later. But if we want to be more rigorous, we can keep the actual expression that contains all powers of this frequency difference in time, which will look, I think this was our dashed line. Then we have other terms of perturbative that look less aggressive, doesn't ramp up. And then we used to have exact quantum solution, which is even less aggressive and sometimes goes down. And the, how does it call it? Lab report, humble homework is to take the value of like this perturbative expression at certain time, let's say 100 femtosecond, and tabulate it as function of incident weight. To expect that to see how it will practice the resonance condition and how it will peak when it is resonant and off resonant. So what we are perfect in time. So what we did today, we were living a simple life. If derivation of equations can be called. So our general strategic goal to organize all efforts in the class are to get quantum dissipative dynamics, which is more challenging, and it needs statistical thermodynamics, density matrix approach. But now we simplified our task, and we took Hamiltonian of light to matter interaction, same as we would do next when we will live a big life. We instead of density matrix equation of motion, we took Schrödinger equation, and we practiced first order perturbation theory instead of second order. So we took like first step in the same direction of describing light to matter interaction or system to bath interaction, well, not bath, system with external perturbation interaction. And we did our first step in understanding how third postulate of quantum mechanics can be violated and still be a bona fide theory. So describing how the occupations of quantum levels can be violated and changed over time through this approximate way. Since this is an approximate theory designed to work only in certain regimes, it definitely violates the normalization. This wave function is no way normalized. But if we are looking on the short time interval, it is okay. And it was used for like from 1925 to 1985 as the primary tool, primary bridge between experimental and theoretical spectroscopy. What else? Schrödinger equation, first order perturbation, and Hamiltonian of light to matter interaction.